there's a general consensus that you all want one on Friday, and I'm happy to be there. But we'll see how we get on. I intend to have those biscuits distributed by the end of the day, so I don't want to carry them around anymore. I've given up on the 100%, but you never know. I might get one now. In which case you confirm them. But we'll see. So you've all had a chance to actually look at this, hopefully, and you've all done it between Friday, when we saw it, and now. Well, you've had 5 days, sort of thing. 4.5. And you're all going on the lecture slides after you've done them, so you should all have the answer. And let's see. I don't believe that. That sort of that would be that could possibly work because 33 responses rather than 25% each.
Simulate polls.
Try it again. Once it's sort of open.
We're going home Monday because I work on this. I'm going to finish work. Basically, come back yeah, no, I got work Thursday and I got work Monday. Otherwise, I wouldn't. You're not coming in? There's nothing Thursday. There's no lecture Monday. Yeah. No one already comes in. No, I'm not. I've got a one-on-one with him, right? That's about it. You don't
We all went there to do the process stuff. I'm not feeling now, but I should
I'm scared because I might have to say what.
Okay. Well, the answer was number 2. And basically, the way to go about it is obviously something like this. So you basically find out first how long it takes to actually get to 1,770 meters. Well, you multiply through by 2, so that's 3,540 meters. X squared. Then you've got x squared equals 3,540 divided by 9 point whatever that is. 8.1. And that basically gives you seconds squared. If you do that, you end up with roughly 90 point something seconds. So 19 seconds. And basically, what you've got now We worked out how long it took to actually get to the ground, so about 19 seconds. This is the formula that gives you the actual distance traveled, and we said, well, because it's sort of a formula, it looks something like this. And after 19 seconds, we want to know what the speed is of the object, basically. So what we need to do is take the derivative at that point. So if that is our f of x equals this part, so f of x equals a half gx squared, then f dash of x is simply g times x. Now we know we want the speed at 19 seconds, so what we do is plug in the 19 and get 9.81 times 19, and that's roughly, whatever the answer was, 186 meters per second. So that was the speed at which that object hit the ground. Roughly. Okay. So we've got some more rules that we're not going to prove, but might be quite handy to know. And we'll have examples of that in a second. So we've got the chain rule, which is very easy. So we've got effectively we've got f of x equals x plus 3 all squared. Then that's effectively the same as f of x is equal to g of h of x, where h of x is equal to x plus 3 and g of x is equal to x squared. So what you're ending up with if we just differentiate this, well, if we work this out, x squared, x plus 3 all squared is x squared plus 6x plus 9. So the derivative of that, if we do it this way, is just 2x plus 6. If we did it this way, using the chain rule, then we've got f dash of x is equal to g dash of h of x times h dash of x. Now, g dash is 2x, so that basically means we've got 2 times x plus 3 in here, times h dash of x is just 1, which basically is 2x plus 6, same thing. So that's just an example of how you would do that. Simply, the inverse rule, again, we'll use it in a second. Derivative of sine and cos is basically cos of minus sine respectively. And this is an interesting one, which we're going to use in a second as well. The derivative of e to the power of a times x is a times e to the power of a times x, which has got an interesting corollary, basically, that if f of x is equal to e to the power of x, then f dash of x is equal to e of x. So this function is its own derivative. So it's quite an interesting case. So those are the ones that we won't prove, but are quite important. So I've already given you an example of the chain rule. So obviously my example was fairly trivial. I was going to work it out by just multiplying this out in anyway. But if you've got some higher powers, then that becomes a bit unwieldy. So you're better off using the chain rule, because that's much easier to do. And here we can work out the inverse rule to differentiate what the derivative is of the square root of x. Well, we know that the inverse of that would be x squared. So we can work out the derivative of that quite easily, because that's just 2x. And then using the inverse rule that we have, f dash of x, which is the derivative of the power of the square root of x, is equal to 1 over the derivative of g f of x. And if you plug that in, well, that's 2x, so 2 times f of x, 2 times the square root of x. Now, last week we showed that f of x equals x to the n. The derivative of that is f dash of n times x to the n minus 1. So some people might say, well, actually, we've already proved something similar. If we just replace our n by a half, then we have f of x equals x to the half, which is square root of x. So we've already shown that this is basically a half times x to the half minus 1, which is a half times x to the minus a half, which is equal to a half times square root of x. Except, while this is effectively the answer that we're getting here, we didn't actually prove this to be the case for fractions. We only proved this answer for n is an element of the natural numbers. So we can't really use that result, at least not the proof that we have for it, to show this. However, we'll see in a second that we can actually prove this result in general. Here's some more examples. If we want to work out what the derivative is of 2 to the power of x, then we'll observe that 2 is the same as the natural, it's e to the power of the natural logarithm of 2. So I know what the derivative is of e to the power of something. So if we replace 2 to the x with e to the power of the natural logarithm of 2, then we get this expression here. So this is just replacing 2 with what the natural logarithm of 2, e to the power of the natural logarithm of 2 means. And then by using the laws of powers, basically that's just the same as e to the power of x times logarithm of 2, which we've already described in general what the derivative is of that. So we can just plug this into the formula we have to get the actual derivative of that, which is effectively to the power of x, the derivative thereof is equal to the derivative of this expression. So we're just moving the natural logarithm of 2 at the front and leave the rest. So we've worked out our derivative. And if we wanted to work out the derivative of tan of x, then we just observe that tan of x is basically the same as sum of x over cos of x, and use the quotient rule. So we find that it's 1 over cos squared. So these are just examples of all these rules that we've come across previously and just applying them. So what you might find in the exam is that I might ask you to derive something, and so you should just be able to apply these rules. In the interest of time, I think rather than you guys going through this, I'll show you this basically myself. So what we want to show is that if f of x is equal to the natural logarithm of x, we want to show that f of x is equal to 1 over x. So if you've done derivatives at school, that's probably something that you were told was the answer. We've now got all the ingredients to actually prove that ourselves. So using the hint, basically we set g of x to be e of x, which is the inverse of this function here, the exponential logarithm. And we know what the derivative is of this, which is just equal to e of x. Okay? So we can then use the inverse rule to say that f dash of x is equal to 1 over, and the inverse rule basically says it's g dash of f of x. Now, g dash of x is e to x. Well, basically, that means we're dividing over 1 over e to the natural logarithm of x, and that's simply 1 over x, which is what we want to prove. So this is basically just applying the hint, working out the derivative thereof, and then using the inverse rule to actually work out the derivative. Does that make sense? Also blank slide. Everyone come across the natural logarithm of x? Yes? No? No? Well, basically, if you have a number 4, you can divide it as e to some number, where e is 2.71, 8, blah, 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 all to some power a. Okay? So that's basically what e represents. E is just 2.71, it's the Euler constant. Raising that to some power to get 4. So it'll be 1 point something or something. Natural logarithm basically just gives you a. So natural logarithm of 4 is whatever that power needs to be. That's basically what the natural logarithm represents. And if you draw the graph, let's see whether I've got internet access. Let's see. Doesn't look like it. So this is what the graph looks like. And the derivative basically gives you is 1 over x. The derivative of that just looks like this. So, well, obviously just this part, because that's what it's defined on. So there we are. So that's quite an interesting relationship between the natural logarithm and 1 over x. Now, having shown that, we can now basically show exactly what was done over here. We've sort of said, okay, we've got x to the power of n, and what we want to know is the derivative thereof. And at the moment, we've proved it for n being part of the natural numbers. But now we can actually say this is true not just for n in the natural numbers, but for any power of x if that is part of the real numbers. So if you actually write what we've got there, so f of x is equal to x to the power of r, where r is element of the real numbers this time round. What we want to show is that f dash of x is what we would like it to be. So r times x to the power of r minus 1. And that's what we want to show. So using the hint, writing x to the r, and we can just say that's equal to e to the power of natural logarithm of x to the power of r. So that's basically just rewriting x as power of e. And using the laws of powers, that's the same as r times ln of x. So what we've got now is we've got a chain rule that we can apply. So we're setting already, so let's see. So g is e to the power of x, and h is r times the h of x. So g of x is this, h of x is r times natural logarithm of x, and you can now work out the derivative. So g dash of x is e of x, h dash of x is r times 1 over x. This is the result we just worked out. So if we now apply the chain rule here, so f dash of x is equal to g dash of h of x times h dash of x, then that's just g dash of x is just itself. So that's e to the power of r times ln of x times h dash of x, which is r times 1 over x. Now that's equal to r times x to the power of r times 1 over x, which, I'm running out of space, is equal to r times x to the r minus 1, because this x cancels with one of these r, which is what we want to prove. I don't know whether you guys can actually see that on here, but visible as well. So basically, this sort of rule that you probably know from school, where n is any number, and the derivative basically is n times x to the n minus 1. We've just proved that for the general case using pretty basic rules. So that's basically all we need to know about differentiation. So you might ask, what's the point? Basically, differentiation will allow us to do a huge class of problems which are interesting for optimization purposes. So you want to try and find out the maximum size of something given certain constraints, or the maximum volume of something given certain constraints, and that basically can be worked out using differentiation. And we'll have an example of that in a minute. So in order to do that, we just need to introduce two more concepts: local minima and local maxima. Basically, when we've got a graph like this, then these points here, where basically we can draw a line at this point which is parallel to the x-axis, are of special interest. This one is a maximum for sort of fairly obvious reasons, in the sense that at this point, basically, the graph goes up, reaches the maximum point there, and then starts declining again. And similar, this one is sort of minimum, because the graph is sort of declining here, sort of decreasing, reaching a minimum here before it goes up again. So, in terms of derivatives, what we can see is, you can think about this as a sort of car traveling at a certain speed, slowing down, and basically reversing. So if this sort of distance traveled, it sort of increases the distance, and then it sort of reverses, basically goes back. So at that point, it needs to decrease its speed to 0, and then start reversing, so going backwards. So at that point where it sort of changes directions, obviously its speed is 0. And that's what the derivative at this point will work out as. So the f dash of x0 here, x0 is roughly here, will be 0. And that's how we work out those points of maximum and minimum. So they're turning points, because they go from a positive value to a negative value. And if you think about the derivative, at these points, basically this is where they cross over the x-axis. So in terms of local maximum, if you look at this graph again, and what we've got here is a maxima. There will be an interval at which point this point up here, the maximum, will be bigger than everything in that interval. So if you just look at an interval around here, then this point here will be the biggest one in that interval. Obviously, if we extend that interval from going from here to over there, then that wouldn't be the case anymore. But we're just looking for an interval that holds. So the interval, if we pick it just around this area here, at that point, this point will be the maximum value. And similarly for the minimum. So we're picking an interval from C to D such that f of A basically will be the maximum value in that interval, and local minimum if there's such an interval such that f of A is smaller than everything else in that interval. And it's got a turning point, which is basically just a generic term for a minimum or maximum. So, and the turning point is, again, very obvious because it's changing directions. So it's turning around. So it goes from speeding up to reversing, from reversing to speeding up again. So that's a turning point. So, and those points are the bits where we can find solutions to optimization problems, because they'll give us the largest value or the smallest value of something that we might be interested in. And with differentiation we can work them out, because we're looking for points where the derivative is 0. So as an example, we've got this now. So let's draw this to make this slightly more real. We've got a parcel, and this where it shows I can't draw. There's our parcel. And the perimeter of the base, so this is A, B, and the height, being this bit. So the sum of the perimeter of the base and its height is less than 96. And we're now saying if the base is square, so instead of having A and B, we've actually got A and A here. What is the largest parcel in terms of its volume that we can send through the post? Okay, so how do we do that? So first of all, we translate what we've got here. So the constraints are perimeter of the base and its height. It's less than 96 centimeters. So, well, if this is and since we're dealing with sort of functions, we might as well call this x. So let's call this x now. So what we've got 4 times x plus h needs to be less or equal to 96 centimeters. And the volume of this parcel is just basically the base, so the volume of the parcel, and you find out in terms of x, is x squared times h, which is basically just the base times the height. That gives us the volume. So what we want now to do is we want to find the biggest parcel in terms of volume that we can send through the post that satisfies these constraints. Well, what I've noticed here as well is that the maximum size of our base can obviously be just 24, because if the height is 0, then the biggest x we can have is 24 to get up to 96 centimeters. So 96 divided by 4 is 24. Obviously, a parcel of 0 height is pretty useless, so that's the maximum values we need to consider. So, and obviously, if the base is 0, then the maximum height would be 96 centimeters. But again, it would be a pretty pointless parcel to have with no actual base area. But in that sense, what we need to have is our x is strictly greater than 0, because at 0 we've got no parcel, and it's strictly less than 24, because if it's 24 we've got no height, so again we've got no parcel. So we want to find the maximum value that our volume can take given those constraints. So obviously what we could do is run a little program that sort of runs through all possible values of x and sort of starts approximating this thing, which is how you would probably do it if you didn't have a clue how to solve this otherwise. So you could basically write a little for loop, which basically churns out different values of x, plugs it into this formula to work out a h, works out the volume, keeps track of how big the volume is so far, and then comes up with an answer. That's a possibility. So basically, that would give you a quick idea of what sort of value we're looking for, because at some point the volume will be increasing, and then suddenly it will be decreasing again. So you will find at some point that you've passed that maximum value that you're looking for. But we are better than that, because we can say, okay, well, we'll start off with saying we might as well use the biggest possible value, so 96 centimeters, in which case we can write our h as a function of x. So h is 96 minus 4x. So that's basically how we would work it out. We can now plug that into our volume here. So volume of h, the volume of x is x squared times 96 minus x squared, minus 4x, sorry. So we can work that out. That's 96 x squared minus 4x cubed. And we now want to find the maximum value. So if we just again, let's see if we plot that. Google being our friend, so we do that with minus 4x cubed minus, what was it? 96x squared. We should see that being an interesting graph between. Okay, can I use this? Yeah? Sorry? Oh, sorry, yeah, plus 96. Yes. I was wondering why that suddenly was just negative. It didn't really make sense. So, plus. Yes, so this is more likely. So basically between 0 and 24, we can already see that at 0 obviously the volume is 0, at 24 the volume is 0. But in between, we're getting to this point here, which is roughly maybe 16. So we're getting, probably at 16, we're getting some sort of maximum. Let's see whether that visual inspection actually turns out to be the case. Okay, so let's see. Basically what we want to find out is the derivative of this function, and we need to set it to 0. So what's the derivative of b dash of x? Is what? So basically we've got just no polynomial here, so we can just use the rule that we had over there. So 2 times 96 is 192 x minus 12x squared. Everybody agree with that? That's basically doing that on the whiteboard. So, and what we want is basically we want to find out b dash of some x0 needs to be equal to 0. Well, if you plug that in, so 0 equals 192 x0 minus 12x0 squared. Then we can take the x0 out. 192 minus 12 x0, and that needs to be equal to 0. Well, the first obvious answer is x0 equals 0, which, well, basically, since we assume that our x values lie between 0 and 24, strictly between 0 and 24, that's not really an answer, so we don't want that one. So the second possibility is that 192 minus 12x, 0 is equal to 0. And lo and behold, if you do that, basically bring the 192 on the other side, or well, the 12 on the other side, so you've got 12x0 equals 192. So divide everything by 12, and that gives you 16. So 16 is indeed the point that we sort of guessed at by looking at the graph. Yeah? What do you mean, sort of factorize? Basically, we did factorize here, so we did, yes, basically we just took the x0 out. We're just factorizing it. It's x0 minus 0 times the other factor. So we worked out x0 is actually equal to 16, which is what we got from the graph anyway. We can now work on the height. We plug in 16 here, so our height is 96 minus 64. So So our height is actually equal to 32, if I'm not mistaken. And we can now work on the actual volume of the thing. And it's actually equal, so the maximum volume we get at x0 is equal to 16 squared times the height that we worked out, 32. So that's equal to 256 times 32. And what about it? 8,192 cubic centimeters. So that's the maximum parcel size that we can set. That's the optimal one. So it's the biggest one given the constraint we have. So that's how we work this out. And yes, here's the graph basically, so maximum being here. So so that's an example of how we focus on. Basically, that's roughly what you'll have to do for the example in the exam. Here's another piece. So if our function was actually something complicated like this, x cubed minus 6x squared. Again, if you want to work out the local minima or maxima, you take the derivative, which is basically just applying the normal rules that we've got, so it's 3x squared minus 12x plus 9, and then solve for f dash of x equals 0. So we plug that in. So for which values do we get 0? So we can divide both sides by 3, giving us x squared minus 4x plus 3. Doing your factorization at this point, basically looking at, okay, what are the factors of 3? Well, it's plus or minus 1 or plus or minus 3. You try out which ones work. You find that it's 3 works, so 9 minus 12 is minus 3 plus 3 is 0. So x minus 3 is a factor. If you plug in 1, 1 minus 4 is minus 3 plus 3 is 0 as well, so x minus 1 is another factor. So you factorize your polynomial, and you know that the answers are, we have local maxima or minima at 1 and 3. Now, the question is, which is which? Which is the local maxima, which is the local minima? Well, if you plug in the value, f of 1 is 25 and f of 3 is 21, that doesn't tell us very much whether or not this is a maximum and this is a minimum. So, and the easiest way, obviously, is you can just ignore the thing, in which case you can just read it off. So, x cubed minus 6x squared plus 9x plus 21. And sorry, at 1 and 3. So we can see here at 1 we've got a maximum, and at 3 we've got a minimum. But instead of, because obviously you won't have necessarily the time to draw the thing, you'll need to find a cleverer way of doing this. And the cleverer way of doing it is by looking at the derivative of the derivative. So, and if you do that, then the second derivative of a maximum will be negative. And the second derivative of minimum will be positive. Anyone has got any idea why that might be? So, if we draw the graph of something like this, okay, so we've got a maximum and a minimum. So, what we know is the derivative at this point will go through here and will go through here, because it's 0 at that point and 0 at that point. So basically, what's the derivative going this way? It's positive. So basically, we're getting a positive derivative going all the way through here, hitting 0, and then it becomes a negative one, because this is now a sloping thing, so it goes down all the way here. Until, whoops, it's a little starts increasing again, and basically goes through here again. And at that point, basically you can now see that the slope at this point is negative. So if I took the derivative of this part here, now the slope is negative, so it'll be somewhere down here. And if I look at the slope here, it's positive because it's going up, so it'll be somewhere up here. And that's basically how you can decide. And the next graph, basically on this page, will draw this slightly better. So we've got the original graph, and the derivative is drawn here. So you can see at this point it hits 0, and at this point it hits 0 again. And the derivative of this part is this line here. So at the minimum it is negative, at this minimum it is positive. Okay. So if you take the derivative of this part, you just get 6x minus 12, plug in the numbers, f double dash of 1 is minus 6, which is somewhere down here. And f double dash of 3 is 6, which is somewhere up here. So you can tell that x0 equals 1 is the local maximum, and x1 equals 3 is the local minimum. So this is now for you guys. Have a go at solving this part using the same techniques that we've got. So I'll start you off. So we've got a window. Semicircle here. Of radius R. got this area here. It's a half of pi times r squared, which is equal to a half pi times x over 2 squared plus r is just halfway. And the length of that's the area of a semicircle, and the perimeter of the semicircle is given by a half pi times 2r, so that's equal to a half pi minus x. And what we want to ensure is that the overall perimeter of the whole window is a maximum of 4 meters. So we call that P of x. Well, that's basically x plus 2h plus the perimeter of this thing, a half times, and that must be less or equal to 4 meters. So we set it to 4 meters because that's what we want the maximum to be. And we want to maximize the area of the window. So the area of the window is h times x, giving us this bit, plus this half circle there, plus, if you work out a half of pi times x over 2 squared. So that's the area. This is what we're going to maximize. Okay, so what we need to do now is effectively get rid of that h, because that's annoying us because we can't differentiate it. What we want to end up doing, just like with the partial solution, is we want to be able to differentiate this function with respect to x, and then set it to 0 to work out what the local minimum or maximum is. But we've got a h in there which is not going to help. So, but